Welcome to the deep dive. Today we're tackling something truly mind-bending. We're looking at source material that tries to bridge two fields you almost never hear mentioned in the same breath.
That's right. We're talking quantum physics, super precise, dealing with the fundamental nature of reality and, well, human memory, which is notoriously slippery.
Exactly. And we start with maybe the most famous number in physics, the speed of light. 299,792,458 meters per second in a vacuum. It's, the cosmic speed limit, the bedrock.
The thing that defines causality, how events unfold in time. You can't beat it.
Or so we thought. Because the work we're diving into today hinges on the fact that scientists actually have manipulated it. They've slowed light right down even, stopped it completely.
Which sounds like science fiction, but it's documented laboratory physics.
Right. And the conceptual framework for our deep dive comes from this really detailed paper. It's called the Hau Correlation, Quantum Interference, Information Coherence, and Collective Memory Divergence.
Quite a title.
It is. The author is a scientific investigator, Justin Lake. And he's done something pretty bold. He's using these breakthroughs in quantum optics, literally controlling light as kind of analogy, a model for these widespread inconsistencies people report in collective memory.
What people often call the Mandela Effect, right?
That's the popular term, yeah.
Yeah.
Collective memory divergence is the more formal phrasing Lake uses. Now, we need to be super clear up front, and Lake himself is very explicit about this in the paper.
Absolutely critical point.
We are exploring an analogy, conceptual bridge. This isn't about saying, the lab experiment caused people to misremember Nelson Mandela's death. Not at all.
No. The goal here, as Lake puts it, is to use the sort of established scientific rigor from quantum optics to create a scientifically rigorous platform for interdisciplinary discussion. It's about finding a new language, maybe, to talk about these memory phenomena.
Okay, so let's dig in.
Yeah.
Why is this juxtaposition, this specific analogy, so compelling? Why use light to model memory?
Well, think about what light is. Fundamentally, it's our primary way of getting information about the universe, isn't it? From distant stars to the signals in fiber optic cables, it sets the timing, the coordination for everything.
It underpins causality itself.
Exactly. So Lake's core idea, the jump-off point, is this. If you can demonstrate control, even distortion, over the ultimate information carrier, light itself, within a perfectly controlled quantum system.
Then what does that suggest, even theoretically, about how information might be perceived or recorded or remembered across large groups of people, especially in our hyper-connected world?
It opens up questions about information fidelity, about the stability of the data streams we all rely on. It's a pretty profound starting point.
Okay, so to really get the analogy, we first need to understand the physics experiment that inspired it. This isn't just theory. This is real-world stuff done by Professor Hau and her team.
Yeah, groundbreaking work starting back in the late 90s, mostly at Harvard and the Roland Institute.
And the source material reminds us, Einstein 1905, special relativity. Light isn't just fast, it's the cosmic rulebook. It dictates the sequence of events, makes sure cause comes before effect everywhere.
It's the synchronizing pulse of the universe in a way.
So if light carries the information, if it is the signal,
then being able to mess with it, even in a tiny lab setup, opens a conceptual door. Lake argues it hints at the possibility of, as he puts it, alteration of data in its original form.
Meaning changing information before it even gets stored, whether that's in a computer or maybe in our head.
That's the conceptual leap, yeah. The idea that the fidelity of the information itself might be vulnerable at the transmission stage. It's a mind-bending idea. Hashtag tag 1.2 Hau's breakthrough experiments.
So how do they do it? How do you stop light? You need a pretty special environment, right?
Oh, absolutely. You need something called a Bose-Einstein condensate, a BEC.
Okay, I know it involves making atoms incredibly cold, like colder than deep space cold. But what's the key thing about a BEC for stopping light?
It's more than just cold. It's about reaching a quantum state. You cool certain types of atoms, bosons, like sodium or rubidium, down to billionths of a degree above absolute zero, just incredibly cold.
Colder than anything natural, basically.
Right. And at that temperature, the atoms basically stop behaving like individual particles.
Yeah.
Their quantum wave functions overlap, and they effectively merge into one single giant quantum entity.
A superatom.
Exactly. The whole cloud of atoms acts in perfect unison, totally coherent. And it's this macroscopic quantum coherence that makes the light-stopping trick possible. The BEC isn't just holding the light, it's actively participating in the quantum process.
Okay, so you have this perfectly synchronized quantum superatom. How did they use it to slow light down to, what was it, 17 meters per second? That's like bicycle speed?
Yeah, that was the first big result in 1999. They used a technique called electromagnetically induced transparency, EIT. It sounds complicated, but the core idea uses quantum interference.
Interference, like waves canceling each other out.
Sort of, yeah. You shine two lasers onto the BEC. A coupling laser puts the atoms into a special quantum superposition, a dark state, where they physically cannot absorb light from a second probed laser beam that's carrying the light pulse you want to control.
So the BEC, which would normally absorb the light, suddenly becomes transparent to it.
Right, that's the transparency part. But here's the really clever bit. Setting up this EIT state drastically changes how the light pulse travels through the BEC. It creates what physicists call a very steep dispersion curve.
Okay, steep dispersion. What does that mean in practical terms?
It means the group velocity of the light pulse, the speed at which the peak of the pulse travels, plummets massively. The medium acts like incredibly thick treacle, but only for that specific light pulse under those EIT conditions.
So from 300 millimeters per second down to 17, that's an insane reduction, almost 20 million times slower.
It really shattered assumptions about how much you could slow light inside a medium. But then 2 years later, they went even further.
They stopped, parked it.
Exactly. The 2001 paper. This is the real key for Lake's analogy. They managed to halt the light pulse completely.
How? If it's moving at 17 meters, how do you hit the brakes?
They did something really elegant. While the slowed light pulse was traveling inside the BEC, they slowly turned off the coupling laser. Remember, that's the laser holding the atoms in that transparent superposition state.
Okay, so you turn off the condition that allows the light through.
And the quantum state of the system changes. The light pulse doesn't just vanish, though. Its information, the specific quantum state encoded in the photons, gets transferred. It's mapped onto the collective spin state of the BEC atoms.
So the light's message is imprinted onto the matter itself.
Precisely. The energy and information of the light pulse are stored as a stationary excitation within the coherent superatom. The light is effectively paused, held in the atomic memory of the BEC for a short time, milliseconds, in the experiments.
And then they could retrieve it.
Yes. By turning the coupling laser back on, they reversed the process. The stored atomic excitation was converted back into a light pulse, which then exited the BEC, carrying the original information, apparently with no measurable loss in fidelity.
Wow. So they decoupled the information from light, held it in matter, and then put it back onto light. That's that ability to pause information flow, to create a break in time for light itself. That's the core physical phenomenon Lake is using, right?
That's the absolute crux of it, this controllable, reversible, temporal discontinuity in the propagation of the universe as fundamental information carrier.
Okay, so now we shift gears. We move from the physics lab to the analogy. We need to unpack the quantum concepts Lake uses as the bridge to memory.
Right, and the big one here is coherence. Hashtag 2.1 quantum information and fidelity.
We mentioned the BEC is perfectly coherent. In physics terms, what exactly is coherence and why is it so vital for information?
Think of coherence as perfect synchronization. It's about the phase relationships between the different quantum wave functions in a system. Are they all marching perfectly in step? In the BEC, all the atoms' wave functions are phase-locked.
Like an orchestra perfectly in tune.
That's a great analogy. If everyone's playing in tune and perfectly timed, in phase, you get a clear, pure note that information is transmitted with high fidelity. In quantum computing, maintaining coherence is everything. Lose it, and your calculation fails.
So what's the enemy of coherence?
Decoherence. It's what happens when the quantum system interacts with its environment. Little bits of heat, stray magnetic fields, any kind of external noise. These interactions knock the components out of phase. The orchestra starts playing out of tune, the information gets scrambled.
Okay, so how does the light-stopping experiment relate to decoherence? They controlled the process.
Yes, it was controlled and reversible. But Lake suggests we can model it conceptually as a kind of controlled decoherence event. You're deliberately interrupting the smooth, continuous phase evolution of the light wave. You're breaking that perfect synchronicity, even if only temporarily.
So the act of pausing and restarting, even perfectly, shows how sensitive the information is to the continuity of its phase.
Exactly. The experiment demonstrates that the integrity of the information, the light pulse's state, depends entirely on maintaining those precise phase relationships, first within the light itself, then within the atomic spins storing it.
So if we take this metaphorically, what does phase relationship correspond to in terms of, say, collective memory?
Well, if you think of collective memory or shared perception as a huge distributed information network, coherence could represent the state where everyone in the population has synchronized access to the same version of a fact or event. The phases are aligned.
And fidelity means we all remember it the same way, matching the actual record.
Right. Decoherence, or what Lake terms phase drift in his analogy, would be like a subtle desynchronization creeping into that network. Even a tiny interruption or shift in the underlying information signal could cause the remembered output to drift slightly away from the original input across the population. Hashtag tag 2.2 temporal discontinuity.
And the fact they introduced a temporal break pausing the light seems really important here too.
It is. Photons fundamentally encode space-time events. Halting a photon, even briefly, means you're physically interrupting that encoding process. You're decoupling the information from its expected place in the flow of time.
And the source material mentions that even theoretical modeling of this process shows it's incredibly sensitive, that stopping and restarting could introduce tiny, maybe unavoidable phase offsets.
That's right. Even if the retrieved pulse looks identical, the very act of interrupting its temporal journey creates a potential vulnerability. The models suggest that the phase of the retrieved light might be slightly shifted relative to where it would have been if it hadn't been stopped.
A tiny temporal hiccup.
A tiny hiccup, exactly. And for Lake's analogy, this is key. If information propagation is this sensitive to controlled interruption in a near-perfect quantum system,
Yeah.
then how much more vulnerable might our big, messy, real-world information systems be? Systems like global communications or even collective human memory.
That's the core question the analogy forces us to ask.
Okay, let's bring in the other side of the equation now, the human element. We've got this idea of quantum fragility, phase shifts, temporal breaks. How does Lake connect this to why large groups of people sometimes remember things incorrectly? Hashtag 3.1 defining the Mandela Effect. We're talking about collective memory divergence or the Mandela Effect. Lake defines it pretty carefully. It's about these widespread instances where large numbers of people share a specific memory, often confidently held, that just doesn't match the verifiable historical record.
Right. The classic example being many people remembering Nelson Mandela dying in prison in the 1980s when he actually passed away in 2013. But there are countless others, movie lines, brand names, historical details. So what's the standard explanation for this in cognitive science? It's not usually quantum physics, right?
Definitely not. The mainstream view comes from memory researchers like Daniel Schachter, who talks about the sins of memory ways our memory systems naturally fail us, or people like Roediger and De Soto, who study false memories.
And their explanation is basically,
That memory isn't like a video recording. It's reconstructive. Every time you recall something, you're essentially rebuilding it, and that process is prone to errors. Things like suggestion from others, confusing the source of information, merging different memories. These are common cognitive glitches.
so shared false memories, like the Mandela effect, are seen as these individual cognitive errors getting amplified because we talk to each other, we read the same potentially flawed things online.
Exactly. It's seen as a failure or a feature, depending on how you look at it, of the human cognitive system itself, amplified by social networks and information sharing. The errors originate in our heads, not necessarily in the outside world's signals. Hashtag 3.2, the curious temporal alignment.
Okay, but here's where Lake introduces his correlation, the Hau correlation. He points out something, well, intriguing, though he stresses it's purely hypothetical.
Yes, this is the observation that gives the paper its name.
He notes that the widespread discussion and reporting of these collective memory divergences really seem to take off, to become a noticeable cultural phenomenon in the early 2000s.
Right around the same time that Lean Hau's light-stopping experiments were being published and discussed in the scientific community and even popular science.
Now, again, Lake is extremely careful here. He states, this is just an observation of timing, no causation claimed. It merely, quote, invites conceptual exploration.
He puts it in footnotes, emphasizes the hypothetical nature. It's a point of synchronization that he finds interesting enough to build an analogy around.
But hang on. The obvious counterargument, and surely the most logical one, is the internet, right? The early 2000s is exactly when broadband exploded, when social media started, when platforms emerged that allowed millions of people to suddenly realize they shared the same quirky misremembering.
Absolutely. That's the standard and, frankly, very compelling explanation. The internet didn't cause the memory errors. It just made them visible on a massive scale for the first time. It allowed aggregation.
So we don't need quantum phase drift to explain it. We just need Google and message boards.
That's the conventional wisdom, and Lake acknowledges this counterargument directly. He's not trying to disprove the cognitive or sociological explanations. Instead, he's asking if the nature of these shared errors, the way they seem systemic, the way specific details seem slightly shifted rather than randomly wrong, might benefit from a different conceptual lens.
So the internet is the amplifier, making the errors visible.
But maybe, Lake suggests, the vulnerability, the reason these specific kinds of systemic feeling errors occur, could be conceptually modeled using the Hau experiment's demonstration of information fragility.
So it shifts the focus slightly. Instead of just, why do our brains make mistakes? It asks, what if the very information streams our brains are synchronizing with are susceptible to subtle, systemic phase inconsistencies that only become apparent when amplified globally?
Exactly. It reframes the problem from purely a cognitive malfunction to potentially an issue of systemic information integrity input. It's a provocative reframing, using the physics as a metaphorical tool. Okay, so now we get into the real meat of Lake's analogy. How does he map these quantum ideas' coherence, phase drift, onto something as vast and messy as collective human perception and digital information systems? Hashtag 4.1, analogical link to collective memory. The first step is to view collective perception, shared knowledge, even cultural memory, as a kind of enormous distributed information network. Like the BEC, its stability relies on some form of phase alignment or synchronicity.
Meaning we all need to be working from the same data sheet, essentially.
In a sense, yes. If the network is coherent, the collective memory is stable and matches the record. Lake then proposes that the controlled interruption in Hau's lab serves as a conceptual model for how systemic divergence could occur in this larger network.
So people are constantly receiving information from media, the internet, historical records presumably transmitted via light-speed signals at some level. If there's a tiny inconsistency, a phase shift in that foundational signal, how does that become, say, remembering Berenstain Bears instead of Berenstain Bears?
The idea is that our brains reconstruct reality based on these input streams. If the input itself carries a subtle systemic phase error, maybe a tiny timing difference in when related pieces of information arrive, or a slight spectral distortion, that error gets integrated into the memory consolidation process across many people simultaneously.
Okay, but a tiny error should just be noise, shouldn't it?
Individually, maybe. But Lake's argument hinges on amplification. When millions of people integrate that same subtle inconsistency and then share and reinforce their slightly off memory through social and digital networks, the minor input drift gets magnified into a major, confidently held collective discrepancy.
So it's quantum-level fragility in the signal, potentially amplified by mass communication, into a perceived reality shift.
That's the core of the analogical link he's drawing. Amplification of subtle input phase drift leads to macroscopic output divergence. Hashtag 4.2, information synchronization in digital systems.
And this brings us back squarely to the early 2000s context. Lake connects this not just to human memory, but very explicitly to the digital infrastructure that exploded then.
Yes, this is crucial. Our modern world runs on fiber optics. Global finance, communication, data storage, GPS timing, it all relies on transmitting pulses of light over thousands upon thousands of kilometers with incredible precision.
And these systems depend on near-perfect synchronization.
Absolutely. Trillions of pulses per second. But light signals traveling through fiber aren't perfect. They experience dispersion, different colors traveling at slightly different speeds, and attenuation, signal loss.
So they need repeaters, amplifiers.
Exactly. The signals have to be constantly regenerated, amplified, and crucially retimed at regular intervals along the cable. And every retiming step, Lake suggests, introduces the possibility of a minuscule clock drift. Tiny, but potentially non-zero.
Ah, okay. So this is where the hypothetical drift comes in. If every node in this vast global network introduces a tiny potential timing error.
What's the cumulative effect? Lake proposes the concept of cumulative desynchronization. Over vast distances and potentially over time, these tiny, almost imperceptible phase drifts in the light-based timing signals could accumulate across the network.
So it's not like the internet breaks down, but the overall synchronicity might subtly degrade.
That's the idea. It wouldn't necessarily cause catastrophic failure, but it could lead to a situation where different parts of the global information system are slightly but measurably out of phase with each other, or perhaps with a true historical baseline.
And this desynchronization in the digital realm, the foundational information layer,
Could then manifest as inconsistencies in the data archives, or perhaps influence the perceptual synchronicity of the humans relying on that data. The master record itself might subtly drift. It's a fascinating, if slightly alarming, concept.
So the Mandela Effect, in this analogy, isn't just people misremembering. It's potentially a reflection of a subtle instability or drift in the underlying informational substrate we all depend on.
Right. The divergence isn't necessarily an error purely in human cognition, but perhaps a symptom of the informational environment itself struggling to maintain perfect coherence over planetary scales and time.
And this leads to his most speculative idea.
Indeed. The notion of systemic resynchronization, Lake throws out the possibility, again, highly speculative, that if these cumulative desynchronizations become too large, the entire informational network might undergo a kind of rapid, subtle self-correction, a recalibration.
Like the whole system snapping back into a new, slightly different coherent state.
Sort of. The observed memory discrepancies in this view wouldn't be errors per se, but maybe the echoes or artifacts of the system settling into a new, slightly revised, present moment or accepted historical state. The inconsistency is the evidence of the system trying to regain coherence, potentially by subtly rewriting the baseline reality it presents to us.
Wow, that's a really big idea. The informational layer of reality periodically rebooting itself.
It's definitely out there, conceptually speaking, but it follows logically from the premises of the analogy he sets up.
Okay, let's try to pull the threads together. We've gone from atoms cooled near absolute zero to potential glitches in the fabric of shared reality. What are the main takeaways from Lake's framework, built on Hau's physics? Hashtag 5.1 synthesis of key analogies. First, the physics gives us information storage and separability. Hau showed light's information can be detached from light, stored in matter, and retrieved. Information isn't immutable. Its integrity depends on the medium and the process.
That's point one. Information is conditional. Second, decoherence sensitivity. The experiment and the theory behind it highlights how incredibly sensitive information fidelity is to phase relationships. Even tiny controlled interruptions or environmental noise can potentially degrade or shift the data. Phase integrity is paramount, and it's fragile.
All right. And third, applying this to the big picture. Vulnerability of collective cognition and communication. If we model our large-scale information systems, both human memory networks and digital networks, as being dependent on phase coherence, then they are inherently susceptible to the amplification of small systemic inconsistencies, or phase drifts, over time and distance.
Those are the three pillars of the analogy, connecting the quantum experiment to the large-scale phenomenon. Hashtag 5.2, the importance of the boundary.
Now, we have to reiterate that boundary again. Lake isn't saying the physics causes the memory effect.
Absolutely not. And it's critical listeners understand this. Lake is meticulous about this boundary. He's providing a language, a conceptual toolkit borrowed from quantum optics terms like coherence, phase drift, temporal discontinuity, to analyze systemic information failures in a new way, one that goes beyond standard cognitive models.
It's about offering a different explanatory framework, not a causal mechanism.
Precisely. He's saying if information encoded in light, our fundamental carrier, can be experimentally halted and potentially phase shifted, then it opens the conceptual possibility that all data transmitted by light could, in principle, be subtly modified during propagation.
Even though doing that on a large scale is way beyond anything we can currently do.
Exactly. He acknowledges that manipulating global information streams this way is far beyond current experimental capability. That anchors the speculation firmly in the realm of analogy, while still allowing for the exploration of its conceptual implications. It gives a potential physical grounding for why systemic shared errors might occur, even if we can't yet prove the physical link.
It seems the real value here is that it offers a way to think about why millions of people might make the same specific error, rather than just explaining why individuals make errors in general.
That's a good way to put it. It addresses the systemic and content-specific nature of some collective memory divergences, which standard cognitive models sometimes struggle to fully explain beyond suggestion or convergence. Hashtag 5.3 suggested research avenues.
So, being a scientific investigator, Lake doesn't just leave it at analogy. Does he suggest ways to actually test this framework, even indirectly?
He does. He proposes moving the analogy into controllable, measurable systems, but not necessarily human brains. He suggests interdisciplinary experiments focused on testing the core mechanism of phase drift amplification.
Like what kinds of experiments?
For instance, designing experiments using quantum networks or complex computational models. Could you intentionally introduce controlled decoherence or tiny cumulative phase shifts into the synchronization signals of these artificial systems?
And then see if the system's output Its memory or data processing starts to diverge systematically from the original input in ways that mimic the proposed phase drift.
Exactly. If you could show that subtle, accumulating phase shifts in a light-based communication system do lead to predictable systemic errors in data fidelity or pattern recognition within that system, that would lend powerful support to the core principle of his analogy.
So you test the mechanism in a controlled, non-human system, which then strengthens the plausibility of the analogy for human systems. Clever.
It's a way to bring scientific rigor to testing a conceptual bridge without making unsupported claims about direct causality in human memory. Hashtag tag outro.
So Leanhau's incredible work showed us we can gain unprecedented control over light, the very medium of information. We can slow it, stop it, pause its journey through time.
But this deep dive into Justin Lake's Hau correlation suggests a flip side. While physicists achieve perfect control in the lab, our vast global information systems might be grappling with a kind of inherent, unavoidable phase drift, a constant, subtle struggle to maintain perfect synchronicity.
A fragility amplified, perhaps, by the very interconnectedness that defines modern life.
Yeah. We base our entire sense of shared reality, our history, our science, what happened yesterday, on the assumption that the information arriving is stable, coherent, perfectly synchronized, that light travels true.
But if quantum optics shows even fundamental constants can be manipulated, that information flow is sensitive to phase down to the quantum level.
Then what does that really imply about the long-term stability of the enormous light-speed networks, both digital and cognitive, that we rely on for consensus reality? Are they as solid as we think? Or are they more plastic, more sensitive to these subtle drifts than we've ever considered?
It certainly makes you think. So maybe the next time you encounter one of those moments, a memory that feels absolutely right but clashes with the record, something shared by many others, perhaps consider this. Is it just a quirk of the mind?
Or could it just possibly be an echo of our reality's underlying informational fabric undergoing a subtle, continuous process of resynchronization? Our reality defined not by perfect stillness, but by a constant, delicate dance to maintain coherence against the background noise of phase drift.
A fascinating and perhaps slightly unsettling thought to leave you with. Thanks for joining us on The Deep Dive.